This is going to be the fifth and final video in this particular series where we've been working our way through the sheet of trig identities. Today we're going to do product to sum and sum to product formulas. If you look back at the sheet we've been working through, other than the bottom, which is law of sines and cosines, we did that back in triangle trig. And the other two sections, the red complex numbers and the pink expansions, those are for different days, different subjects. You can worry about those in calculus and pre-calc. But today, as far as the identities go, we're going to wrap it up with all of these, which finishes the top part of this chart. Not definitely, again, not a chart you need to have memorized. Can't think of anybody I know who does, but you should be aware of them, and the more you use them, the better you will be at using them. So we're going to do a couple of problems and then one identity. A typical problem, at least from our book, to use these formulas would be to change a multiplication into an addition or an addition into a multiplication. This might be useful in solving. We're getting ready to start trig equations soon. And for instance, if you have an addition and you can turn it into a multiplication, that might be something that will help you solve that particular equation. We'll have to see those as we come to them. So let's start with this. And what if we want 2 sine 4.6 times sine 7.2 to be a sum instead of a multiplication? I want you to notice in our textbook, these identities are written kind of differently. Instead of having the 1/2 over here, we have a 2 over here. So any of these could be written like that. With that gone, just multiply both sides by 2. I'm going to think of it that way right now because of the problem that I'm working on. So I have 2 sine A sine B. 2 sine alpha sine beta, as those are the Greek letters that the chart we're working with uses, will be equal to cosine alpha minus beta minus cosine alpha plus beta. All right, again, I'm not really changing it. I'm just moving the 1/2 to the other side and making it a 2 to fit the question I'm asking. And in this particular question, I'm going to say that alpha is 4.6, beta is 7.2. So my expression should be equal to the cosine of alpha minus beta. So that's the cosine of 4.6 minus 7.2 minus the cosine of alpha plus beta, 4.6 plus 7.2. And really, I've just substituted in numbers in their place right now. Nothing fancy has happened. 4.6 minus 7.2. I should be able to do that real quickly. Not sure how quickly I can do that. That difference is negative 2.6 minus the cosine of the sum. And 4.6 plus 7.2, that one I can handle. That's 11.8. Okay, so we've made it, in the instructions say sum or difference, so we're okay with it being a difference. The one thing it does specify, though, is we need positive arguments, meaning the thing you're taking the cosine of in each instance needs to be positive. So I have a cosine of a negative 2.6. If you'll recall, cosine is even, meaning if you put negative 2.6 or positive 2.6 in, you get the exact same result. So I can just simply change to negative or to cosine of positive 2.6 minus cosine of 11.8. And that now is in sum or difference form. So we went from multiplication to addition, subtraction. All right, so what about going the other way? What if we need to transform this difference into a product? So it's going to be very similar, just working backwards. I am cosine alpha minus cosine beta at this point. So here's the one I want to use. Cosine alpha minus cosine beta. Alpha is 2.4. Beta is 4.4. So the result would be negative 2 sine of alpha plus beta over 2 times the sine of alpha minus beta over 2. And then I just need to simplify a little bit. So that's negative 2 times the sine of 2.4 plus 4.4 would be 6.8. And then half of that would be 3.4. And then this other term, 2.4 minus 4.4 over 2. So that would be negative 2 over 2, which would be negative 1. Okay, so again, we are in the spot we were in a few minutes ago where we had a negative argument and we did not want to because the instructions say positive arguments only. In the last problem, we just ignored it because the cosine of one number is the same as the cosine of the opposite of that number. Sine is odd. The sine of 30 is the opposite of the sine of negative 30. All right, so if I want to get rid of that negative 1 right there with the inside the sine argument, then I need a negative sign outside. I already have a negative at the front of this whole expression, so that negative, along with the negative that it's going to happen when I change the argument to positive 1, will look like this, the whole thing positive. Okay, so long story short, if you have a negative inside a cosine like up here, just ignore it. Get rid of it if you don't want it to be there. If you have a negative inside a sine, get rid of it, but tack on an extra negative when you get rid of it, and two negatives make a positive. So now that I've jumbled that all up, and get rid of some of those, and there we go. All right. So there's two types of problems, changing from products to sums and vice versa, which you might expect with the title of this section, sum to product and product to sum. So let's do an identity. I definitely want to start on the left here. Remember, pick the more complicated section. If I started on the right, tangent of 6x, I have no idea what to do. All right, but if I start on the left with the more complicated stuff, it's easy to simplify complicated expressions. It's easier to do that than to just dream up something to do to simpler expressions to make them complicated. There's a million different things you could do on the right, but if you look at the left, it should make more sense of what to do. Also, remember the section you're in. We're talking about taking sines and cosines that are added and turning them into products. So if I look at the numerator and denominator on the left, I should pretty easily figure out what to do with them. So let's consider the top. Sine something plus sine something else. So I'm going to be using this, and I'm going to use the plus because of I've got a sum here, which means I'm going to have a plus first time and a minus the second time. All right, so this expression on top should equal 2 times the sine of a plus b over 2. So that would be 5x plus 7x, which is 12x, over 2, which is 6x, which appears to be conveniently turning into the argument over here. But to finish that up, I need to multiply that by the cosine of alpha minus beta, a minus b over 2. So for me, that would be negative 2x over 2 or negative x. All right, 5x minus 7x is negative 2x. Divided by 2 is negative 1x. The bottom is a cosine A plus cosine B. All right, so I'm going to use the middle in between my two blue circles up there, my two blue ovals. Cosine A plus cosine B equals 2 times cosine of A plus B over 2. So A plus B is 12x divided by 2 is 6x. And cosine A minus B over 2, a minus b over 2, same thing, negative x. Okay, so this is going to get real simple real quick. 2's can cancel. Cosines can cancel. And I'm left with sine 6x over cosine 6x, which is equal to tangent 6x, which is what we wish to prove in the first place. All right, so this is going to be a little bit shorter one. You're used to working with identities. We're just going to finish up the page, learn our last few, and move on from there. All right, so that's going to do it. Young's out.